For the afternoon session. So our next speaker is Jian Ding, who's going to tell us about percolation for level sets of the Gaussian field on metric graphs.
Thank you for the introduction, and thanks for inviting me. So today I'm going to tell you something about percolation for level sets of Gaussian fields on metric graphs. This is based on joint work with a second-year student at University of Pennsylvania, Matteo Wirth. The plan of this talk is I will describe the problem to you, and I will describe our result, and I will give a fairly, I hope, relatively convincing sketch of the proof, and then we'll discuss a few related questions and discuss the potential application of our approach, and also point out some challenges that our approach on its own doesn't seem to be able to address. Okay, so that's the plan. Let's first set up some notations and definitions. I will be rather brave because for this audience, I don't think there's much point to define Gaussian fields so carefully. So let's denote by Vn to be a box in Z2, where with the side length 2n and centered at the origin O. And let Gn tutor is the metric graph on Vn, that is to say, Gn tutor equal to Vn union with En. E sub n here is the edge set. I need to be a little bit more careful. Here for each edge, I not only treat it as a graph theoretical edge, but also an edge corresponds to an interval which contains a collection of points. So an edge is basically a collection of many vertices. You can view it that way. And eta and v, for v in this metric graph, this is just a GFF on Gn tutor, let's say with the Dirichlet boundary conditions, which is usually the condition we take. For those who know discrete Gaussian field but do not know what is a Gaussian field on the metric graph, here is a simple explanation of what eta is. It can be obtained from, you can first, in order to sample a Gaussian field on the metric graph, you can just first sample a discrete Gaussian field. And then, for each edge, we sample independent Brownian bridge conditioned on the values you have at endpoints. So this is introduced by Loop in a work in 2014, where he used this to prove a very beautiful theorem that couples the Gaussian field to the random walk loop soup at criticality as well as to random walks. And I want to say that this has been considered independently by Zhai a bit later, roughly speaking, half a year later, and similar results have been derived too. And when I say percolation for level sets of Gaussian field on metric graphs, what do I mean? Well, we can just treat this as a bound percolation. Well, we say each edge E is open if all the points, the Gaussian field for all the points on E is larger than a certain threshold lambda. For some threshold we take, I wanted to give a remark that at the first sight you may think it's more natural to consider the percolation, vertex percolation that comes from discrete Gaussian field. I want to argue that in Z2 actually the level set percolation on the metric graph is as natural, at least because due to a work of Aru, Loop, and Superveda, they showed that the first passage set on the metric graph converges to that of the continuum Gaussian field. So this is actually indeed a very nice object to study. And for the result I'm describing here today, I don't think there's any difference if you consider the percolation on metric graph or consider the percolation just on the vertex percolation for discrete Gaussian field. But the techniques is much more clean if we consider the percolation for metric graph. And there will be some technical annoying things to do if you want to convert that, which we didn't do. But I don't expect in Z2 consider percolation on metric graph or on Z2 or on the integer lattice would make a big difference. But the story will change if you consider the percolation in Z3 or higher dimensions, because there's supposed to be a sharp transition for the percolation, and in particular, the threshold for the transition will be different for percolation on the metric graph or percolation on the integer lattice. But that's for higher dimensions. In Z2, we don't expect such differences. Anyway, that's just a remark. Our result will be on the percolation for the metric graph. And the object we are going to study is the chemical distance. And here's what we show. There's a question mark in the timeline, and this question mark is strongly correlated to the next question mark I'm going to give you. The result says that for any fixed threshold we take, that's why in Z2 you take lambda to be 1, to be 0, to be minus 1. We don't see qualitative difference in the behavior. But this is not the case in higher dimensions again. For any fixed lambda, and let's consider alpha, beta, gamma, which is between 0 and 1, and any epsilon that is positive, we claim there exists a constant C such that the limit soup of the probability of the conditional probability that the distance, we are considering the distance between boundaries of macroscopic annulus. Let's look at the distance between boundary of alpha n and the boundary of beta n. We claim that the probability for this to be larger than n times log n to the power of 1 over 4, given that the boundary of alpha n and the boundary of gamma n is a little bit outside, is connected, this probability is less than epsilon. Let me give first a remark which would clarify the result a bit more. Combined with Aru, Loop, and Superveda, in this paper, they had a preprint on arXiv already, but they're going to split it into papers which they're going to show a lot of nice things about first passage set for Gaussian fields. They're going to show the convergence of the first passage set in the metric graph to the continuum, and then as a consequence, they can show the percolation probability, the probability that the alpha n boundary and the gamma n boundary are connected. This probability is strictly between 0 and 1, and in particular, this is going to be continuously depending on alpha and gamma. since they told us that they are only going to finish their paper by 4, and after I know that, I tried to prove this continuity of the percolation probability separately. After a day or two, I decided we better wait. It's not obvious how to do such things. It's a bit, yeah. I even asked help from Vincent, and in the end, we decided patience is better here. This also says that their work really proves something pretty interesting and fundamental, because they use the convergence to derive something that for discrete, which you use all sorts of techniques in discrete, it seems to be a headache to prove. Anyway, it's very intuitive that this should be the case, yes. Say that again? Sorry, chemical distance is the graph distance in the percolation cluster. Yeah. So, but if we combine that, which is, I don't know, they said 4, one of the authors said coming in 4, one of the authors said by the end of the year, I don't know. So this is a question mark, and that question mark really depends on this, because we want to combine the result to give you something stronger. Then we can assume beta equal to gamma. Because if we know that this event occurs with roughly similar probability if beta and gamma are close to each other, then you can just replace beta by gamma by taking a limit. Previously, in a work with Li, we have shown, okay, I don't want to write the whole thing, but probability that dimension is less than 1, that's not good. Probability that the distance between alpha n and beta n boundary, this distance is larger than n times e to the log n to some power, say 0.6. This probability goes to 0 as n goes to infinite. Sorry. This probability is strictly positive for all n. Comparing this result with the previous result, the improvement are twofold. Here we only show that the distance is bounded by something with a positive probability. But in the new result, we show as long as you have percolation, then with high probability that the distance is bounded by something. Also, the bound is sharper. Here is n times some exponential of some power of log n. And this, by the way, this comes from a estimate of Makarov's theorem, where it's a fundamental ingredient for the previous proof. In the new result, we sharpen the power. We sharpen the distance to n times log n to the power of 1 over 4. Well, you need at least the n, right? So this is sharp up to a small power of log n. It's not completely obvious that you get an upper bound like this. In fact, we thought this should be superlinear, and we thought this should be at least n times log n, and we spent quite some time trying to prove that, and then we failed, and we started thinking on the opposite direction. And at this point, it becomes tantalizing to decide whether this distance is actually linear or not. We don't know. Our method doesn't seem to be able to decide that. But it's also quite subtle now that the room of error here is pretty small. So if you want to show it's superlinear, seems you have to do a very refined estimate. I don't know how to do that. So that's in my opinion, a pretty interesting open problem that probably requires some clever new idea. So is the description of the result clear? Yes?
The graph distance is the distance in the original graph. It has nothing to do with the symmetric graph.
The chemical, okay, to take a percolation, what is the chemical distance? Is like, for each edge you have, it can be open or closed. You remove all the closed edges.
Yes, but when you introduce metric graph, each edge is replaced by n edges or something?
Say that again? Each edge is like 1, the distance. Each edge counts 1.
Okay.
if in the percolation cluster you have a path, the minimal path goes through this number of edges. That's this number is the distance. Is that clear now?
Okay, so metric graph is just you adding some vertical.
Okay, maybe you are confused by the metric here. This is just the terminology that I don't know. Either Loop introduced or I think he took it somewhere. You could also call it a cable system. Then maybe that clarifies. This metric there's no metric in this metric graph. Is that what confused you? There is? Okay.
You haven't edged already putting an interval there, so that point.
Not in the way that we like, at least. I don't know. I view it as in each edge you just consider there's a continuum of path and there's a continuum of points connecting it. Always give me difficult time. What's the metric, by the way? Yeah, but that's pretty trivial. It's not interesting. Okay, so I hope the description of the result is clear. Now let's move to the proof. I will cheat in a few places, but I hope to convey the main idea to you. For simplicity, you see, I will start cheating already. Consider lambda equal to 0, and let's assume that the field on the alpha m boundary is always 1. Let's be condition on that. Of course, this happens with probability 0, but once you see how to do the proof in this case, to extend it in the real case, it just requires a little bit more carefulness and some technical work. So the main idea is the same with this assumption. So let's assume that. Just make the argument a bit more clear. And let's also have a few notations. Let's write mu equal to gamma plus 1 over 2. So this is larger than gamma, larger than beta, larger than alpha. And let's drop the subscript of n in the notation. And also just use d for the distance. Now, let's introduce an observable, which is just the average of the Gaussian free field on the boundary of mu n, which is the outermost box I'm considering, but still a bit away from the boundary condition that we're taking. The key idea in this proof is to build in a martingale and study the intrinsic structure of the martingale. The martingale is a Dubos martingale of x, taking conditional expectation of x with respect to a certain exploration process. And the exploration process is, if you think about it, very natural. We just start with I0 to be the boundary of alpha n, and let IT to be the metric board in tuta Gn of radius t. So we just take IT is just all the points. IT is random naturally. IT is all the points so that the graph distance from the alpha boundary is less equal to t. Maybe at this point I should give you a lemma. This exploration process has the feature similar to the stopping time, meaning the following. For any open set U that contains I0 and T non-negative, we have whether IT is contained in U or not is measurable with respect to FU, where FU is the sigma field generated by all the etas in U. FU is just all the information you get from looking at the Gaussian free field at set U. just means whether IT is in U or not, it depends on the field on U itself. This is like a stopping time feature of this exploration process. And if you picture how you do the exploration, this is very clear this should be the case. Especially if you discretize it and run the algorithm, you can convince yourself this. Given this, we can then define a martingale, MT, which is the condition expectation of our observable, given what we have explored up to time t. Now, what I'm going to do next is to analyze this martingale and relate this to the chemical distance. Before that, let's introduce a few more notations. Let the harmonic measure VUK to be, we start a Brownian motion at V. The Brownian motion here is not a Brownian motion in the plane. It's the Brownian motion in my metric graph. So it moves on these lattices and also the edges between the lattice points. The Brownian motion on G tilde, his K for the first time at U. And for simplicity, let's write HMT VU to be HM VU with respect to IT. Well, I guess, yeah, the Brownian motion also will be killed at the boundary. Because that's when I define the Gaussian field with the direct boundary condition, the random walk or the Brownian motion will be killed when it hits the boundary. That's how we define the Green's function here. And let's introduce yet another notation. This is just the average of the harmonic measure if we take a random point from the boundary of mu n. Yep. With these notations, it is trivial from the harmonic extension property of Gaussian field and also lemma 1 that MT is just the sum over all the boundary points of IT, and look at the harmonic average of eta u. And in particular, this has to be greater equal to 0 because my IT, all the points in IT has non-negative values. So the harmonic extension on IT certainly is greater equal to 0. This is one simple but important observation for us. So this controls the value of the martingale. It has to be always positive. But the martingale also has quadratic variation, right? The quadratic variation of the martingale at time t. This can be, we are looking at the Doomb's martingale. What's the quadratic variation? You look at the difference of the conditional variances. So that is the variance of x given your initial condition, subtract the conditional variance of x given the condition that you have at point at IT. Now we write d of alpha beta to be the distance between alpha boundary and the beta boundary, just for simplicity. Let me prove another lemma. I mean, suppose that we have percolation, which means suppose that alpha n and beta n boundary are connected to each other. What can you say about this martingale? can the martingale has to be positive. That's what we know, right? It has to be non-negative. But can the martingale get really close to 0? It cannot, right? Because this is what the lemma says. Exists a constant such that for all epsilon positive, probability that the martingale is larger than some c times epsilon for all times between 0 and distance of between alpha and beta, given the distance between alpha and gamma is finite, given this is to say given percolation. This is with high probability, with probability at least 1 minus epsilon. And why is this? Let's draw a picture. This is my martingale MT. This is my axis T. This is my value of the martingale. So here is the distance between alpha and beta. Here is the distance between alpha and gamma. Suppose, well, my martingale starts at 1, right? Suppose at some point before distance between alpha and beta, my martingale drops to some value that is very small, c times epsilon. At this point on, how likely is for the event to occur? The event is the martingale will stay positive until this time, right? This is not very likely because if you do a calculation, the quadratic variation is of order 1. The quadratic variation between d alpha beta and d alpha gamma is order 1, because once you explore even further, the variance of your observable has to decrease by a constant, no matter how that occurs. So that means no matter what happens, this quadratic variation is bounded from below uniformly. As a result, if your martingale ever touches a very small value, the probability for it to survive all the way till the time you want it has to be very small. But we are conditioning on the event that this happens. As a result, as a result, the martingale cannot be getting close to 0. This is like if you're conditioning on the Brownian motion to stay above 0, then the Brownian motion cannot hit a point that is very close to 0. If you start the Brownian motion a bit higher than 0. That's the kind of intuition. Except there's one layer of complication is here with the time. We need to convert the time to a quadratic variation of the martingale, but that comes from lemma 2, and a simple calculation coming from two-dimensional Gaussian field. You just look at the conditional variance. Okay, so I almost have everything, but I still need a couple of lemmas. There's a couple of lemmas I essentially proved in Loop's paper. I'm going to first state it and continue assuming it. If I have time, I will come back to it and explain how to prove it using the martingale I gave you. Yeah?
How do you know that the chance that the martingale goes below epsilon at some point decays linearly in epsilon? So that's what you're doing.
Because is there a quadratic? You think it's a root? No, I think it's linear. The probability for Brownian motion starting at epsilon to stay above 0 for time 1, I think it's epsilon, right?
Yeah.
So that's linear then.
So it's the same.
Yeah. For us, we don't need the linear relation. We just need this to be anything that goes to 0. That's enough for us. Okay, let me state another lemma, and then I will try to put everything together. This lemma says how many number of points, lattice points, you're going to explore in your IT. This is bounded by the number of lattice points that is connected to the upper boundary, right? And this essentially, I can't remember whether Loop actually did this calculation or not. In his paper, he calculated the probability for 2 points to be connected to each other. from a point to a boundary maybe requires a bit of work, but let's give the credit to him anyway. The number of points that is connected to the alpha boundary, this is order of n squared over square root log n. The probability for a point to be connected to a boundary is 1 over root log n. That's what we need. And also, typically, such point has value. Well, typically such point has value as if there is no conditioning. This requires a bit of work, but if we combine the martingale approach we are using, this is not too hard to show. Basically saying, even if the point, the value of the point is high, the increase on the probability to be connected to the boundary is smaller than the increase is dominated by the decay of a Gaussian variable, because for a Gaussian variable to achieve a value that is higher, there's a Gaussian decay. But the increase of this probability is much smaller than Gaussian decay. So that means if you look at the typical point that is connected, the value is just what you would expect, meaning order of root log n. So let's assume on this board, I'm going to assume even something a bit stronger than lemma 4. In lemma 4, we can get actually tails on the number of points. We can get the expectation we can get the bound on the number of points that are connected to the alpha boundary and also achieve a certain value. But let's ignore that. Let's just assume that all the points that connect to the boundary just have root log n value. I cheated again, but this will not matter if you see the argument. So let's just give the argument assuming this cheat. Okay. I try to finish the argument here. Write AT to be all the points that has ever been the boundary, and also the point is 0, it's positive. Then A1, A2, da da da, AD alpha beta are disjoint. And necessarily they have to be lattice points. So this is one observation. Also, we have, I'm going to cheat, hopefully for the final time, that the quadratic variation at time t plus 1 minus the quadratic variation at time t, this is larger up to constant than the sum over AT of the harmonic measure square. I mean, if you think about it, the difference of the quadratic variation is just the variance of the harmonic extension given a slightly larger boundary of the harmonic extension on the slightly smaller boundary. And if you do the calculation, you can find out this difference of the quadratic variation will be larger than the second moment of the harmonic measure. I cheated a little bit because our exploration process is not also sees things on the boundary. Also sees things in the edge between lattice points. This introduces a certain technical complication. But if you just do a careful bookkeeping, you will arrive at this bound. I'm not going to explain that because that is a little, you have to use a careful eye to check things. And that's not very inspiring anyway. So the point is we can lower bound the quadratic variation per step by the second moment of the harmonic measure. Okay. But I see there's something that I was missing because I didn't tell you something. Let me give you a consequence of by lemma 4, what we get. By lemma 4, and I also need lemma 3, yeah. What does lemma 3 says? Lemma 3 says that conditionally on percolation, MT is always larger than some epsilon, right? And lemma 4 says almost all the values that you're going to explore is of order root log n. That means the harmonic measure for each t, if you look at the harmonic measure on the positive part of the boundary of your metric ball, the sum of the harmonic measure this has to be larger than epsilon times root log n, because the harmonic average is larger than epsilon, and each of them the value is at most root log n. You need at least epsilon over root log n that many harmonic measure to get this contribution of harmonic average. So this is the bound that comes from lemma 3 and lemma 4. Actually, just part of lemma 4, assuming the values is all the root log n. I still didn't use the number of vertices yet in lemma 4. Now, at this point, I can use Cauchy-Schwarz inequality. I have a second moment. Naturally, I can lower bound it by first moment, right? That's what Cauchy-Schwarz inequality is doing. This can be lower bounded by epsilon square over log n times the size of AT. This epsilon square over log n coming from square of this, and the size of AT coming from this is what you would lose when you use Cauchy-Schwarz inequality. Now if we put things together, we know that the quadratic variation.
Jan?
Yeah.
We don't see the board because.
Oh, sorry.
I think it's fixed.
Yeah, we are moved to a different board. It's fixed. I have 5 minutes, right?
Yeah.
I will try to. Yeah, I will try to be quick. But we know that the quadratic variation at time d alpha beta, this is of order 1 because the variance of x is of order 1. So the total quadratic variation is of order 1, but it's lower bounded by this thing. And the quadratic variation, this is lower bounded by the sum from t from 1 of the distance d alpha beta of epsilon square over log n times the cardinality of AT. But we also know the sum of cardinality of AT over t, this is order n square over root log n. Now it's just a simple optimization problem. For each fixed d you take, the best you can do is to choose AT to be all the same for all t, and you get a lower bound. And you want to choose the largest d so that this lower bound does not contradict the upper bound you have, right? And this is just a quadratic optimization problem. This gives the distance between alpha and beta boundary is of order n times log n to the power of 1 over 4. And this is under the events I wanted in all these lemmas to occur, which occurs with hypermobility, conditioned on percolation. So that finishes the argument. The key idea is to analyze the intrinsic structure of this martingale using the fact that the martingale has to stay positive all the time and relate the quadratic variation of the martingale to the harmonic measure. And then you can get a bound out of it. And in particular, we didn't use anything that is specific with the 2 dimensions. We didn't use Markov's theorem, which is a key point of the previous result. Okay, so this concludes the part, the rigorous part I want to tell you about the proof of the theorem in 2 dimensions. In the next 3 minutes, let me quickly tell you some of the other potential applications and related interesting questions that one can think of. In 2 dimensions, I think the most interesting question to me is to decide whether this distance is linear or not. But then you can look at what's going to happen in high dimensions. This framework works in high dimensions too. Actually, in dimension 3, it was known that the critical threshold is 0. But we can give we can compute the exponent of the percolation probability at criticality, and at the supercriticality, we can give a explicit formula for the percolation probability, for the probability that 0 is connected to infinite. And in the subcritical regime, we can get almost exponential decay. What is most interesting is in the critical regime, in d equal to 3. There, even though we can get the correct exponent for the percolation probability, but we lose a root log n factor in this estimate. But this root log n factor actually has important information, which is the following. Look at a Gaussian field on metric graph of 3 dimensions. Say conditioning on the origin percolates to the boundary of a box of size n. Then you look at the cluster. Do you think the cluster should have vanishing or non-vanishing capacity? I mean, can you distinguish between the percolation should basically occur like a single line, or it's more like a percolation? Is a percolation like evolving like a surface, so it has a positive capacity? We don't know, and our method doesn't seem to be able to decide that. That seems to be important in understanding the geometry at criticality in dimension 3, and also this is related to trying to construct a incipient infinite or infinite incipient IIC measure in this case. Lastly, a few weeks ago, Hao asked us a question whether there exist pivotal points for the percolation in 2D on the metric graph. We think our approach can say something there, but it's in progress, so I don't want to tell you the details. I think things are not completely intuitive what's going on there, whether there exist pivotal points in 2D or not. We are still trying to verify things, and some root log n factors are important there, so I don't know. Yeah. So I think my time is up, and I will finish here. Yes.
Yeah, in this formulation, did you use some theorems about martingale, some significant?
No, I didn't use anything significant about martingale except the probability for martingale to stay above 0 is okay. I used if you consider the time inverse of a continuous martingale to give you a Brownian motion, and I used the basic estimates about Brownian motion. I didn't use anything fancy in this proof. It should be. I think it should be all elementary. Yeah. Yes.
So, if I understand correctly, the log n to the 1/4 comes just from the estimate about the number of points in the.
Right.
On the other hand, we know that the structure of the cluster has. The points that are not there will be, it has some fractal structure that sort of the ones that are not there, they will tend to accumulate and things like that. So is there a way to understand that you tried the other direction, but can you...
You mean inverse engineering?
Can you get better than that by sort of improving its...
Yeah, not that I can think. Because this harmonic measure can be harmonic measure of arbitrary curve can be pretty nasty. We are using a very simple band. We're just using Cauchy-Schwarz. You are suggesting improving that somehow.
Yeah, because you know that
Yeah, but that requires pretty strong input so that one can. I mean, in general, we don't know how to control the harmonic measure for some random curve or random clusters. These are difficult. I don't know how to do that. Yeah, I don't know what's the truth either. You think it's rectifiable? You think it's linear? I just don't know. I don't know which. On the even day, I try one direction. On the odd day, I try the other direction. Neither of them come to a conclusion so far.
Any more questions? Okay, so let's thank our speaker again.